Hello students, in this video we'll find the limit of the Stirling formula. In a previous video we showed the limit as n tends to infinity of n factorial over n over e to the n root n. We proved in the previous video that this limit existed. Let's call that limit L. And we showed this limit exists by looking at what? We looked at the sequence dn, which was the log of n factorial minus n plus 1/2 log of n, and then plus n. We showed that that sequence converged to some number over there. That sequence converged to some number c. So of course these things are related by exponentials. In other words, the exponential of c is equal to L, right? So now I can actually use some formulas we know from Calc 2. We're going to use the Wallis formula. So it's the Wallis formula. The Wallis formula says that pi over 2 is equal to the product of the evens, 2 times 2 times 4 times 4, all the way up to 2n times 2n over the odds, 1 times 1 times 3 times 3 times 2n minus 1, 2n minus 1, and then 2n plus 1, like that. Of course, this is the limit as n goes to infinity of this thing. So what can I say? I can say, therefore, the order of the square root of 2 pi, and so this tells me, therefore, that root 2 pi, pi over 2, is on what order? Is on the order of just one copy of these things. I think the square root, they occur in pairs, so just 1 time, or just 2 times 4 all the way down to 2n over 1 times 3 times 2n minus 1, and then the square root of this last thing, square root of 2n plus 1. That's what that tells me. And so now let's do a little bit of manipulation with this quantity over here. So this just means as n tends to infinity, this quantity over here will tend to this quantity. That's a limit expression over there. And so what can I say now? So let's do a little bit of algebra. What I'm going to do is I'm going to fill in 2 all the way up to 2 to the power n. So let's consider this product over here now. 2 times 4 times 2n. And then the bottom I'm going to do is I'm going to do a 1 times 2 times 3 times all the way up to 2n plus 1, and fill in another 2n. So I have 2, 4, da, 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 and then the root 2n sticks around. So I've added in all those powers of 2, so I have to do this thing over here squared. So that's exactly our same expression. This thing's on the order of the square root of 2 pi, pi over 2. All right, great. And so now let's do some algebraic simplifications of this. Of course, I can pull out how many? I can pull out 2 to the n. So this top over here is really just what? The top is really just 2. How many 2's do I have? 2 to the power n. So I have 2 to the power 2n over here. And then I have an n factorial left over. So I have an n factorial squared over, this is going to be a 2n factorial times the square root of 2n plus 1. That's on the order of what? On the order of the square root of pi over 2. And actually we can get rid of that plus 1 over that. That's not going to affect anything. So now we're in the position to do Stirling's formula. So what does Stirling's formula tell me? This says that n factorial is on what order? It's on this order over here. So we're going to fill in that everywhere and see what we get over here. So let's fill in, we can know that the limit exists. So I can replace every n factorial on this scale with an L times this thing. All right, so let's do that. So what we're going to say is we're going to say, therefore, that our expression is on what order? It's going to be on order 2 to the power 2n. Okay, that sticks around. N factorial squared is going to be an L squared. It's going to be an n over e to the 2n. And I'm going to square this thing over here, and that's going to give me just a plain old n over what? Over 2n factorial. So I'm going to replace every n with a 2n. So that 2n factorial gets replaced with 2n over e to the 2n. And then I replace that 2n with a root 2n over here, so I get a root 2n. Great. And then again, as I said, I can replace that 2n plus 1 on asymptotic order with just a 2n, like so. So this thing is on order root 2 pi. And then what am I missing over here? So I'm also missing a what? I'm also missing a factor of L. So I get a factor of L that I'm missing. So I put that down there. Great. Excellent. And so now, of course, this thing with the L squared and the L cancels out. And so what this allows me to conclude is let's count everything over here. So we're going to see what? We're going to see let's see everything that cancels. The first thing that's going to cancel is the L. So I have an L in front of everything. And let's look at the powers of 2. So I have a 2 to the 2n. And down in the bottom, I have a 2 to the 2n, and then an extra factor of what? I have an extra factor of 2. So I have a 2 times 2 to the 2n. Those are the factors of 2 that we have. Let's look at the factors of n that we have. We have a factor of n to the what? we have a factor of n to the 2n in the denominator. So I have an n over here to the 2n. And then n, so the n's are n to the 2n plus 1 in the numerator. So an n to the 2n and then an extra n. In the denominator, there are what? In the denominator, there's an n to the 2n and an extra n. So that all looks like everything's going to sort out properly over there. Good. And then let's see, what do we have over here? In the numerator, we have a what? We have an e, a 1 over e to the 2n in the numerator over there. And then we have a what? Then we have a 1 over e to the 2n in the denominator over there. So those are of the same order over there. Okay? And this thing, of course, is on order what? Is on order the square root of pi over 2. In other words, this whole expression, as n goes to infinity, tends to 2 over pi. Good. So what's our limit? So as n goes to infinity, that tells me that L is going to be equal to what as n tends to infinity? L, as n tends to infinity, has to be equal to what? 2 times the square root of pi over 2, which of course is 2. Now, 2 root pi, and then 1 over root 2 is just root 2 over 2. So this is just going to be a root 2 pi. And so I just conclude over here that L is root 2 pi by the Wallis formula. Beautiful. And so now I can write the Stirling formula in its more traditional form. The Stirling formula in its more traditional form states that the limit as n tends to infinity of n factorial over n over e to the power n times the square root of 2 pi n is equal to 1. And this over here is the Stirling formula. So we prove that the limit exists using some classical analysis results, and then we apply the Wallis formula to show that the limit actually is equal to the square root of 2 pi, and then rearranging it in this form, we get the classical Stirling formula. Thank you very much.